Okay, there's 3 types of continuous data you're going to learn. And uniform, normal, exponential. We'll start with uniform. This is all this blah, blah, blah you're reading from home. Yeah, blah, I read that. Yeah, read it. Okay. All right, hang on, where am I? Let's start with this. Let's start with the story. Ready? You own a buffet restaurant, you know, buffet style, where they go and they fill their plates and they come to the cashier. And let's say you've got this whole salad section. Salad? Can't remember. Yeah. Salad section. And you're trying to figure out the probability of this or that. But here's what's happening. Everybody that comes and brings a salad and has it weighed as they're checking out has always had the weight of the salad, the thing already takes the plate off automatically, between 5 and 15 ounces, and somewhere in the problem it says, and it's uniformly distributed. In a uniform distribution, almost always has that word in there, uniformly distributed. What a huge hint. Know which formula to use. First step, take 1 divided by however many units the range of the uniform distribution is. In this case, all the salads are between 5 and 15 ounces. So how many units are between 5 and 15 if you subtract the two? 1 over 10. There's the first step to get that fraction. Remember, it's 1 over whatever amount the full range of the uniform distribution is. That's the first step. And that number you just calculated, just came up with, is multiplied by whatever amount the question's about. So if I said to you, what's the probability that the next person walking up with the salad is going to be between 5 and 7 ounces, how many units are you being asked about? 2. 7 and 5 ounces is 2 units. Multiply that times that 1 over, what is it, 10?
10, yeah.
110 times 2, you just found the probability for a uniform distribution of continuous data. Let's try another one. Everybody that brings a salad up that always weighs between 5 and 15 ounces, uniformly distributed. What's the probability the next person walks up and their salad is going to weigh between 10 ounces or more? How many units are in the 10 ounces or more? 5, 10 to 15. 5 times what?
1 by 10.
1 over 10. You just found your answer. That's the probability of 5 or more. And that's it. That's why this is going to go a lot faster tonight. I just took this whole 10 slides and broke it down to the simplest format for you. You ready? Here's 5 to 15 is 10 places, so 1 over 10. Okay? That's called your density function that you start with. And you multiply that times expected value variance. We'll get to that in a minute. What's the probability that the next customer has a salad between 12 and 15 ounces? Well, how many units are between 12 and 15? 3. So 1/10 right there times 3, or 3 divided by 10. The probability is 30%. There's a 30% chance that the next person walking up salad is going to weigh between 12 and 15 ounces. That easy. Is that it? Yeah, that's it. We've done 3 of these now. You can calculate any. Oh, wait, let me do one more. I almost forgot. What's the probability the next salad person walks up and their salad weighs between 6 and 12 ounces? Now, I'm not at the end. I'm not at either end. I'm giving you an area in the middle somewhere. Nothing changes, though. How many units are between, what did I say, 6 and 12? How many units are between 6 and 12?
5.
6 units. 12 minus 6. There's 6 units there. Out of the whole thing, 10. There's 6 of them, right? Times 1 over 10. 6/10, 60% chance. Is that right? It's 12 minus 6, 6? I know you said 5. I want to make sure. Right? Or did you say 7? I don't know.
Between 7.
I just went from 6 to 12.
Yeah, but you counted 6. You can't count 6.
Between 6.
That's right. So 6 to 7 is 1, 7 to 8 is 1. Or really just take the largest number minus the smallest. That way you'll never get it wrong. But I just wanted to show you an example where the question's about numbers in the middle and not at either end. Doesn't change a thing. It's the number of units being asked about times the density function, which is 1 over the full range. Too easy. Now, what if I was asking you for the mean? The mean is always the highest number and the lowest number of the range being added together divided by 2. This says it's uniformly distributed between 5 and 15 ounces. So we add 5 and 15, divide by 2. The expected value of this uniform distribution between 5 and 15 ounces is 10. Try another one. Hey, everyone that brings their salad up is always between 3 and 12 ounces. What's the expected, uniformly distributed, what's the expected value? Tell me the math on it. Between how many and how many?
3 and 12.
So you add
3 plus
3 plus 12, which is 15, divided by what? 2, which gives you 7.5 is the expected value in that problem. It's just add the largest and smallest number of the range of a uniform distribution divided by 2. The variance. You are subtracting the range from largest minus the smallest. Then you got to square it. Then divide by 12. Everybody always goes, why do you divide by 12? It's stats. You always divide by 12, and I can look up that answer for you, but everybody wants to go home. So let me make sure you understand that the question is saying it's a uniform distribution, and everybody that brings your salad up is somewhere between 5 and 15 ounces, uniformly distributed. What would be the variance? It's the largest number of the range minus the smallest number of the range, then square it, then divide by 12, 8.33 variance. What if I ask for standard deviation? What would we do now? Square root the variance. That's it. See that variance. A lot of people will square this and forget this divide by 12. That's the most common mistake right here. If it's even on your quiz or test. Your test is, no, that's an important question. Blah, blah, we're still, okay. Okay, what is this? Normal. Next is normal. Look at it. We're 1/3 of the way through already. Want to take a break? Just kidding. Okay. Now, do we remember what normal distribution is? Here's my big hint. We've talked about this a lot. It's Z. That's your normal. It's Z. So, you, I hope, will never do that formula. Instead, you're going to use the Z table, I hope. But just so you know, you could use a formula, but very few people will spend that time doing that when they could just go to the Z chart in your book. But I do want to mention, look at pi's in here. We haven't seen pi this semester yet. Always 3.14159, and we know there's more digits. E is always 2.71828, we know there's more digits. But so you'd have to plug those in, and then this would be the mean and the standard deviation, and then x will be whatever you're being asked about. If you wanted to use the formula, and this formula finds the probability of whatever x is or less, just like when you look it up in the book. You find you're looking up the probability of a number or less. So if this is more than, after you did this whole formula, you would have to subtract from 100%. So I'm just trying to let you know there is a formula. Nobody should be using it unless you just love formulas. But the amount of time to calculate all that on a test, you'd be killing yourself. This looks familiar? All right. All right. We talked about this in length, right? Remember that lecture? I said to you, the mean is 5, standard deviation of 1, and the question's about what's the probability it will be 6 or less. You know just by thinking about the number line that the probability is going to be either less than or greater than 50%. Which is it? Less than or greater than? That's right, because it's going to be on this side of the number line. If it's greater than the mean, the probability of that or less is always more than 50% because it's greater than the mean. It's all, and the mean is always the center number. Right here would be 1 standard deviation greater, 1 standard deviation less, 2 standard deviations greater, 2 less, and way out here is 3 standard deviations greater or 3 standard deviations less. And you can set up the number line once you know the mean and the standard deviations. You can literally set that number line up every time. And you can almost guess what the probability should be, and that's a way to make sure you're looking it up correctly. Here's the hard part, ready? This is the mean is 5, standard deviation 1. Right here, 5.85 is the question. what's the probability that it will be 5.85 or more? Should it be less or more than 50%?
Yes.
That's right. If it were 5.85 or less, then the probability would be for sure more than 50%. But because it said or more, it's above the 50% line, so it's got to be less, or it's got to be less than 50%. Okay, that was a quick review. Let's get to the good stuff. Blah, 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 blah. Look at this. This chapter is too easy. Here we go. Now, a common mistake in figuring out the probability for a normal distribution is someone will calculate a negative z because they accidentally flip the x in the mean, in the numerator. So this is what I want you to remember about this formula. It's always whatever you're being asked about minus the mean in the numerator. Do not take the mean minus what you're being asked about. And that way you'll get to the right z. That's a very common mistake on this z calculation, is flipping those two. You ready? The x, in the numerator, you always want to have whatever number you're being asked to find the probability of minus the mean. And the mean is being given to you in all these problems. And a very common mistake is someone will take the mean minus whatever it is they're being asked about, and they may get a negative z when it really is supposed to be a positive z, and it's all because they flipped that numerator. It's a very common mistake. And then you always have the standard deviations, what you divide by. You find your z, you go to your book, and if the question said, what's the probability of blankety blank or less, you're looking it up like that, there's your answer. If the question says, what's the probability of blankety blank or more, you look it up, and then you go and subtract whatever you just found from 100%. 1 minus whatever you just looked up. So look, that's how this goes. You ready? Pep zone. Now we got to take this a step farther. And this question's a good one. And I want to bring this is something that I've used in real life. Because I was working for this consulting firm, and I went to a lot of businesses in the United States. I'd fly to a different business every week, sometimes 2 in a week, if things went well. And this is one thing that a lot of businesses were having was they either have too much money tied up in inventory, and they're trying to figure out where's the money at, or they keep running out of things, and they're losing sales. And so this inventory management was a major problem. You got to remember, I was doing this in the late 80s. 20-something-year-old punk coming in telling the presidents of companies where they're making mistakes. And these companies are just, maybe they're only doing 10 million sales or 20 million sales, so they're not big. And most of the time, when they bring me in, they're already having problems, and I get there, well, how did you learn how to do that? And they always say, oh, my dad taught me that. He passed away, and now I'm running the business. And they never really had any fundamental business education. They didn't know they could use numbers to make these decisions instead of just this is how I was shown. Very common thing that goes on. It's still going on. This is, what is that, 30 years ago I was doing this? And this is, a lot of businesses still have this situation happening. They just need to realize there's numbers involved. So, this is very real. I've had many companies that have inventory problems just like this. In this case, you're about to read that this PEP auto sales is running out of this item consistently, and so they're losing sales because there's so many auto supply places around. If someone walks in and they're out of something, that sale's gone. They're not coming back tomorrow. They're going to the next auto supply that's probably right around the corner, and they're buying it there, and you've lost it. But at the same time, companies have gone to the extreme to where I do not want to lose a sale. And they over-inventory, and they keep going, we never have money to reinvest in this or to get this done. It's because it's so wrapped up in inventory that it's not free. So there's that balance. Management science, operations management are 2 classes that really highlight it. It's a big part of inventory management is the reorder point. Reorder point, reorder point, reorder point, and in my management science class, I focus so much trying to get those students to realize the reorder point is the biggest part of inventory management. When a product should be reordered. That's the key. And that reorder point's all about that balance called just in time, meaning right as you're running out of a product, that order of that product is arriving on the docks. The last one's being sold. Oh, look at that one. It's being reshelved. That timing is how you keep the least amount of capital in inventory and at the same time not lose sales. And that's usually your optimal inventory turn rate. Managers back in the late 80s, they focused on how do I get more turns? It was all about how do I get more turns? How do I create, it's how often you go through a complete average inventory. That's called an inventory turn rate. And managers were all about, I want more turns, which means less money is being held in inventory. But they took it to such an extreme that they were running out of things. So it's that balance. This problem's really good about this, and I'm going to go a little bit past this example because this is so useful in real life. Any company in your future or currently that has inventory, this is a big deal. So, this PEP auto stores place supplies all kinds of things, including a multi-grain motor oil. When the stock of this oil happens to get to 20, and by the way, you got to remember, in the late 80s when I did this, nobody had automated inventory systems. Nobody had it. So it was all about kind of an inventory person keeping track of things. And that's why it was so hard. But automatically, there could be set up in the inventory system, you set a reorder point at 20. So as soon as someone buys this oil, the count goes down. Someone else bought oil, the count goes down. At the end of the day, the manager of that location runs a report and it lists everything that's hit the reorder point or less. Meaning, it's time to put the order in for all these items. Get it in. And it's all about whoever set that reorder point is who's in charge of that line balance. That's a big deal. Whoever's putting in that reorder point. And that's where I used to save companies tons of money by showing them how to calculate the perfect reorder point instead of just winging it and eyeing it. That was one of the big things I really got to show a lot of companies. So, they're at 20 gallons. It's a replenishment time. But, what if, and it's all about how many of the item will you go through during the time that it takes from the time you place the order to the time it shows up at your docks. That is this phrase left me, the lead time. That's the lead time. It's all about how many, and you gotta remember, you've got thousands of SKUs, thousands of different items. And every one of them has to have this calculation to have that reorder point be exactly as close as you can get to how many you go through during the lead time. And you got to know that lead time. So, whoever we get this oil from is what lead time here? It says the store manager is concerned that we're losing sales due to stockouts while waiting for the order to arrive. It says it's been determined that demand during the replenishment lead time, and a lot of lead times back then was like a week or 2 weeks. Now, things have gotten to where your lead time might be only like 3 or 4 days. But whatever that lead time is, it has a mean. Let's say lead time is a week. Usually, this location goes through 15 gallons of that oil in that amount of time, whatever the lead time is, and with a standard deviation of 6 gallons. First of all, that 6 gallons is not reality because that is a large variation. 6 gallons, that varies when you only have a 15-gallon mean during the lead time. So it's not really reality here, but let's go with it. 15 gallons is what we usually go through during the time it takes from when we place the order for the order to arrive so we can replenish. And if that lead time changes, you've got to recalculate that mean, the standard deviation, to recalculate the reorder point. It's all about the lead time. During that lead time, 15 gallons, 6 gallons, what's the probability that we'll have a stock out? Meaning, right now our reorder point's at 20. What's the probability that we'll sell all 20 and the order has not arrived yet? Which means the next customer comes in, there's nothing we can do. Nothing there for us to put out there and not lose that sale, and we lose it. That's a disaster. And back in the late 80s, when I was heavy into this with companies, we used to always say 10% would be the max chance that you would want of losing a sale. Your goal should be, let's set it for 5% chance of maybe losing a sale. Meaning there's a 95% chance we're not going to lose a sale. And that would be kind of the balance. Some owners of companies would go, you know, I don't want to have that much money set up, I understand the point you're making, but let's go to 10% chance, meaning there's a 90% chance we won't run out. But 10% of the time, there's a good chance, you know, there's a chance you're gonna lose sales. So I used to always try to get companies to go, shoot for 5%. Shoot for 5%. So, and that way you're tying a teeny bit more money up in inventory, but you're losing 5% less sales. So here we go. What's the chances of losing sales? For us to lose sales, we have to sell 20 of them or more. We sell less than 20, we're not losing sales during the lead time. 20 of them or more. Minus how many do we usually sell during the lead time when we did a study on this? During that, we picked randomly 5 days, because we knew the lead time is 5 days. We looked at exactly how many we sold at 30 different periods. And during those 5 days, our mean was how many? 15. Divided by what was the standard deviation on all those samples we took? 6. This will give you your Z. When you go to look up your Z, I put a line through it because I used to do a lot of programming and can't help myself. But when you find your Z, you're going to look that up in the book, and you just found the probability of selling 20 gallons or less. What's the probability of selling 20 gallons or more will be the opposite of what we just looked up. 20 minus 15 is 5. 5 divided by 6 equals 0.83. That's our Z, right? We look up Z in our book, on our thing. We know the left column is always the digit to the left and the first digit to the right. The second digit to the right will always be along the top. So 0.83, Z equals 0.83. 0.83 says 79, a little more than 79.5% chance, almost 80% chance of selling 20 or more. What percent chance is there we're going to run out? The opposite of this, 100%, because this is the percent chance that we're selling, 20 or less. I said 20 or more a second ago, that was a misphrase. 20 or less. We want to know what's the chance of selling 20 or more. Notice I keep saying 20 either direction, because this is continuous data. It doesn't matter. 20 or more, it will be the opposite of this, which means we're at about a 20.5% chance of running out. For most companies, that is far too much risk. That means there's a good chance about 20% of the time you are truly losing sales. And that is a huge amount of money being lost because you've got thousands that are probably this is happening with. All these SKUs, all these separate inventory items. The way, now what you won't see here in the PowerPoint, but in real life what I used to do with companies is say, now that we know Z at 0.83 gets us to 0.20, 0.33, so 33, right? That gets us there. But we don't want that number to be there. We want this number to be there. Or we have that one owner who wants to gamble, we'll go there. At this point in time, the key to this is you put the percentage down, you look up what the Z would be at that percentage, and you work this problem backwards, but you change 20 to X. And you use algebra to figure out what you should be setting that reorder point at. And that's what I showed them. And they said, oh my God, this is revolutionary. We now know what we should be setting that at. And I said, well, here's the bad news. You have 1,900 items that you got to do this with. And reset every one of those reorder points. And that's true. But luckily now everything's on computer, so it doesn't take that long. But back then, you should see their eyes when I'm telling them that. And I take this to the point where I go, now let me show you how much you're losing because you have the wrong reorder points. And that was just one, and it adds up to thousands of dollars. And the reason they got me there is either they're losing money or their profit's so small that they need to figure out why they're not making profit. And this was one of the areas for many companies, was right here, having the wrong reorder points. So, I think, is there an example here of this? We calculated this, we looked it up, it was almost 79.5%. We subtract from 100%. There's a 20% chance that you could be losing sales with a reorder point of 20. Does this tell you backwards? I almost feel like this may show us. We want no more than 5%. I didn't think this was on here. Wow. We don't want any more than 5%. So instead of this being 20%, we want to change it to 5, which means we need to change the 20. We'll make that a variable. We'll work this whole problem backwards and figure out what that should be at to get us to the 5%. So what's step one? We look up the opposite of 5% in our chart, which would be 95%. And we go on our chart. Is that on here? Yeah, all right. We look at our Z chart, and the closest we can get to 95% is right between here. 94.95% and 95.05%. Boy, the Z would be right between them. So we go 1.64 or 1.65. Someone says, why not use 1.645, which would be right between those two. Now we got the Z. And I got to get an eraser here. So it would be Z equals, I'm working it backward, some number minus the 15 divided by the standard deviation. Z equals some number minus the mean divided by the standard deviation. Use algebra to zero in on that x. We multiply both sides by 6. 6 times 1.645. Then we add 15 to both sides. You just found the new reorder point. Now, because we want to lower the chance of running out and losing sales, the reorder point should be slightly higher than 20. We're going to be increasing it, which means we're going to have a little more money wrapped up in inventory, but the money we save and no longer having those lost sales will be larger than the amount of money we have wrapped up in this additional inventory. I'm sorry? Do what?
I want to know where the 1.64 is. Yeah, but where did it come
You ready? Let's go back. You were told that you want the chance of running out to be 5% instead of 20. We got the 20% by subtracting it from the percent we got on there. So what's the opposite of their goal? Instead of it being 20, our goal is 5. The opposite would be 95%. We go up on our table, all those numbers in the middle. Let me show you the real table here, so you can see how many, what we're looking at. Here we go. Where's 95%? Way over here. I'm looking all over here and trying to get as close as I can to 95%. And it's right there. Right there. And so now I'm going to the left. The Z would be 1.6 or 1.65. Right between them, 1.645. Now I use algebra. Now that some calculation got to equal a Z of 1.645. I plug that all in, and then I use algebra to solve for x. And we go back here, and we put it all set up. We multiply both sides by 6. We add 15 to both sides, right, because it's x minus 15. And we end up with 24.87. Now, I know it says reset your reorder point to 25. But I usually say, at least reset your reorder point to 24. Because the one person's saying, oh, that wraps up too much money. Another person's saying, I don't want to run out. Go with 24 then. Now you reset it. Back then, you had to reset the chart, and everybody's got it right there next to each item, what the reorder point is, and that gets down to 20. Now, on computer, all you got to do is go click to reorder point. 20 now is 24. You have that automated system when gallons are going out the door. As soon as it gets to 24, at the end of that shift, it will be on that sheet. You get the order made, and then you won't run out most of the time now. You lowered the risk hugely of running out. What do you think? You lower the risk of running out hugely. You have a little bit more money wrapped up in inventory. 4 more gallons on average are still in inventory, which means that's your money. But the lost sales are not happening anymore. Very rare now.
How difficult is it to get it below 5%?
It's not that difficult. What do you mean? We could just go probably up to 26.
So you're just putting more...
Just putting more money into inventory and reordering sooner. It's that easy, actually. But if you don't do the math on it, some people will raise the inventory or the reorder point too much, or they have it too little. It's finding that balance. And like I said, the balance should be right around in here. Someone who's very conservative goes here, someone who doesn't mind a little risk goes there, but in no way should it ever be 20% chance of running out. That means that reorder point's too low, and you're losing money. And I want to take this one step farther. If a company is selling an item that's rare, where somebody would come back the next day, you want to significantly lower your reorder point purposely to run out. As long as you feel fairly confident that they're going to be coming back the next day or 2 days later to get it, there is a financial advantage to purposely run out. But it's very rare that you have items like that. If you do, it's a back order policy that you purposely run out. The amount of money you save by not having it wrapped up in inventory because they'll come back and get it is significant. And a lot of companies go, I don't want to run out. But you just got done telling me that this is so rare that they're going to come back to get it. You're not going to lose the sale. Not only do you want to run out, I mean, not only do you shouldn't worry about running out, but you purposely want to set your reorder point to run out. Give yourself like a 20 to 30% chance of running out. You're not going to run out all the time, but when you do, you're not going to lose the sale. And you don't have so much money wrapped up in inventory that it's a win-win. So that's how it works in real life. And a lot of companies still are making mistakes there. All right, can we do this? Set reorder points and calculate. And you know how to work it backwards. Look on the chart and find the Z, right? All right, we got 2 done. Man, we're flying. What? What? You might get dinner? What? Where am I here? Solving the reorder point by raising the reorder part from 20 gallons to 25 or 24. On hand, the probability of a stock out decreases from 20% down to 5%, which is the goal. This is a significant decrease in the chance that the Pep Zone will be out of stock and unable to meet the customer's desire to make a purchase. Blah, blah, blah. Here we go, exponential. We're 2/3 through this chapter already. Exponential. You remember how I told you a lot of people mix this up with, anybody remember what was last week, which one? Poisson. Remember that? Poisson was how many between a period of time. Remember, I think the example was a toll booth or something, and it was like, how many, what's the mean amount of cars that go by in a half-hour period? That's Poisson. 2 cars, 3 cars. You can't have 2.5 cars go by. That's Poisson is discrete probability. In continuous, the question would be about the toll booth again and about cars, but the question would be phrased like this. How much time would go by between the next 2 cars at our toll booth? That's the amount of time between an event, and that's exponential. Poisson was how many over a period of time or length or space. This one's all about the amount of time or something, distance, between events. How much time to complete a questionnaire? How much distance between defects in a highway? How much time for a vehicle to arrive at a toll booth or to come here to get gas at this tank or whatever? That's exponential. Because think about the time. It could be 5 minutes. It could be 5 minutes, 1 second. It could be 5 minutes, 20 seconds. There's all these times between numbers. And that's why it's continuous instead of exponential. Or I mean, instead of discrete. Now, the formula is a little different compared to Poisson in that, forget this formula, this is the formula. The difference is 1 minus E. E is always 2.7 blah, 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 right? Everybody knows. E is always. To the power of negative x, whatever you're being asked to find the probability as the x, divided by the mean of the amount of time, or the mean distance, or whatever the mean is in the story. That's the exponent. This calculation you're doing right here will find the probability of any number or less, just like you're looking it up. With this exponential, you're never calculating exactly 3 minutes between cars, or exactly. There's no such thing as a probability of exactly in continuous data with exponential. It's always some number or less, some number or more, It's always a lesser or a more involved, never exact. Like with the other discrete, what's the probability of 0? What's the probability of 1? But with exponential, there's never what's the probability of 0 or 1. It's 1 or less, 1 or more than 1, less than 1. There's always more or less. And that calculation calculates the or less. If the question's about or more, you just put another 1 minus in front of the 1 minus. Now let me save you time. 1 minus e to the power of negative x over the mean. These two cancel each out. You really only need to calculate that if the question's something about or more. You're already calculating the or more when you do this. This is the or more. And that when you subtract it from 1, that's what allows you to get the or less. And so everybody goes, oh, then I got to subtract it from another 1 to get the or more. But you're going back to what you just calculated. So you might as well just say if it's or more, these two cancel out, there's the or more. Or more. Got it? Save you time. No, not negative at all. So it's positive e to the power of negative x over the mean.
So that sign is canceled?
That sign is canceled. It's not being subtracted from 1 anymore because the question is saying or more. Blanky blank or more, blanky blank or higher. To the right of a line of data, a number line, whatever's to the right is being done right here. And that when you subtract it from 1 like this, that makes any number or less with exponential. And so what a lot of people do, especially on Excel, they'll put 1 minus 1 minus, and they'll maybe do the formula, e 2.7 to the power of, and then you just plug in the x. There is an exponential command that we'll talk about in a minute. But you don't have to do the 1 minus if you're doing the formula, because just this part is or more. The e to the power of is or more. So, let's get to our example. We have time between arrivals at this full-service gas pump. And it follows an exponential distribution. That's how you know to use exponential. Almost always say in the story, it follows exponential distribution. Gives it away what to do, what formula to use. Just like uniforms, always in those problems, it will say it has a uniform distribution or uniformly distributed. Gives away what formula to use. Says it follows an exponential probability distribution with a mean time between arrivals at this gas pump of 3 minutes. Remember, exponential never has a standard deviation. Matter of fact, the only problems that have standard deviations is the normal distribution. And that's the big hint that should lead you right to, oh, this is a z problem. It's given me a standard deviation, because none of the other ones from chapter 5 and 6 that we've studied have standard deviation but the normal one, the one before that we just studied. And that's the big hint, because it doesn't say normally distributed in that problem. They won't give away which formula to use unless you go, oh, it's giving me a standard deviation. That should be the click that says, this is a z calculation. All right? If it's giving you the standard deviation, you know it's a z calculation. So it just gives you the mean time. And it says the words, it follows an exponential probability distribution. And you have everything you need. E to the power of what you're being asked about. It's about to ask you if it usually takes 3 minutes. What's the probability that it will take 5 minutes for the next car to arrive, or 2 minutes, or something like that? 2 minutes or more, or 5 minutes or less, or 5 minutes or more. That's your x, whatever the question's asking about. The mu is the mean. It's always given to you. In this case, 3 minutes. You've got to remember to change whatever you're being asked about. What's the probability the next car to arrive will take 5 minutes or more, or 3 minutes or less? Whatever it is, whatever you're being asked about, make it negative, then divide by the mean, and that's the exponent for e. If it says or more, you're done. If it says or less, you got to subtract from 1. Now that's the opposite of everything we learned in all the other formulas. All the other formulas, we had to subtract from 1 if it said or more. This is the only one that you have to subtract from 1 if it says or less. That's the difference. That's the big difference of this one compared to all the ones from these last 2 chapters. Let's get to an example. Hey, Usually it takes 3 minutes for between cars arriving at this full-service gas pump. What's the probability that the next car will arrive in 2 minutes or less? We take the 2 that we're being asked about, make it negative, divided by the mean, which is 3 minutes, so negative 2/3. E is always 2.71828 to the power of negative 2/3. But it said 2 minutes or less, so we subtract that whole calculation of 51% from 100%, or 1. There's a 48%, a little over 48% probability, a little over 48.5% probability of the next car arriving in 2 minutes or less. My question for you is, what's the probability of the next car arriving in 2 minutes or more? And you don't even have to do a 1 minus.
5134.
Yeah, the 5134 is right there. That little part is the old more. And you'd get the same answer if you did subtract it from 1, but you just added an extra step when the answer, you're going to go right back to the answer you already calculated. So that's what I was trying to get across. Okay, now, with this one, I want to make sure we did Excel. We do Excel, and you know what? We got to do Excel on the Z calculation too. I forgot. All right, equals. This is an exponential distribution, so it's EX, it gives you the whole list. There it is, EXPONDIST. If you want to use Excel. But the formula is so easy. It almost takes longer to use Excel than that formula. That's how easy this formula is for exponential. So I go like this, it says X is the first number, which is always whatever you're being asked about. And the example said, what's the probability that the next car coming up to this full service pump will be here in 2 minutes or less? X is 2, comma, lambda. This gets everybody. You gotta take good notes on this one. I'm gonna look right in the camera on this one. Lambda is always 1 over the mean. In this case, it would be, what's the mean time? 3 minutes, so lambda would be 1 over 3. You can literally put 1/3 for the second number, or if you know the decimal, put 0.333 if you want, or something like that. Lambda is always 1 over whatever the mean amount of time is in an exponential problem. So I'm just going to put 1 over 3, comma. You always use a 1 at the end of exponential distribution. Don't use a 0. With continuous data, Excel, for some reason, doesn't even catch it. But there is no exact probability of 2 minutes. Because there's 2.00001 minutes or 1.99999 minutes. There is no exact. They're so close together, it's always either 2 or less minutes, 2 or more minutes, or more than 2, less than 2. And however you state it, because you're using 2, they're all the same. 2 or more than 2 are the same probability. 2 or less than 2, same probability.
Put it at 0, will it give you an error?
It would, no, it should, but it won't. And it doesn't give you the right answer. So just don't use it, or you're going to get the wrong answer. You want to see what will happen?
Yeah.
I'll put a 0 in. Look at that. But watch what happens when I put a 1 now. And you know what? It may give you. There's the real answer. Isn't that something? That's a flaw in Excel, in my opinion. Always use 1 for continuous data, and exponential would be the perfect one to write a rule. Always use 1 as the last number if you're using the Excel function.
So we say X is what the number is?
X is whatever amount, a number you're being asked about. In this case, it was 2 minutes. The middle number, called lambda, is always 1 over whatever the mean is that's given in the problem. And then the last digit's always a 1. So, look at what we just calculated. That exponential, let me go back to the formula. Exponential distribution for 2 minutes or less. When it usually takes 3 minutes, we turned it into lambda, and we got a 1 on the end because we wanted 2 minutes or less. For if the next car arriving, when it usually takes 3 minutes between cars at this full service pump, the probability of the next car arriving 2 minutes or less, about a 48.5% chance. Same thing we got on the Excel when we did the formula. If the question says, what's the probability it will be 2 minutes or more, with Excel, you've got to put the 1 minus in front, because you're not using the formula. So it's just like all the previous things we've learned, 1 minus. But notice, we don't have to change the numbers inside. The numbers in the parentheses in the last chapter had to be the opposite of the question. For this one, you don't have to change the numbers because 2 or less, 2 or more, it doesn't matter. More than 2, less than 2, if they're all the same, so just put the 2. You'd be making a mistake to change that number, actually. So the opposite of 46.5% would be, or 48.5%, would be 51 almost and a half percent. So the probability of the next car arriving in 2 minutes or more is about 51.5%.
What is the other answer giving you then?
2 minutes or less.
No, the 0. Like what, I'm trying to figure out what it's even giving you.
It's giving you the probability of everything right around the number of 2 minutes. But we don't,
Which isn't even right.
it isn't right. That's right. It's been that way for, even back when I used to use Lotus before Excel was invented. That was the same error.
Now you just gave your age away.
Thank
Okay.
you. That's right. I'll give my real age away. I remember when Lotus first came out. How's that? And I want to tell you, there's hardly any difference between Excel and Lotus. Lotus was the dominant spreadsheet when it first came out. Every business was using Lotus 1, 2, 3. And then Excel came around, slowly took over the whole market. And what's nice about Excel, there's a lot more things you could do with Excel because of all the built-in functions that Lotus 1, 2, 3